For centuries, science saw the universe as a grand, intricate machine. It was like a magnificent clock, wound up at the beginning of time and left to run its course. This idea was built on a powerful concept, causality. Causality simply means that every effect has a cause. Push a domino, and it falls. The push is the cause, and the fall is the effect. Scientists like Isaac Newton believed this principle governed everything in existence, from the smallest speck of dust to the grandest celestial bodies. It was an unbreakable law, a fundamental rule of the cosmos that made the universe predictable and understandable. This view, often called classical physics, gave humanity a sense of profound control. If you knew the position and speed of every particle in the universe at one moment, you could, in principle, predict the entire future. You could also reconstruct the entire past. The future was not a mystery waiting to unfold. It was already written in the present state of things. This deterministic vision painted a picture of a universe that followed a script, a story where every line was predetermined by the one before it. There was no room for chance, no space for true randomness. Every event was just a link in an infinitely long chain of causes and effects. Imagine a perfect billiard table stretching out to infinity. If you knew the exact angle, speed, and spin of the cue ball, you could predict the outcome of the break with absolute certainty. You could foresee where every single ball would end up, no matter how many times they collided. This is how classical physicists viewed the universe. The laws of motion were the rules of the game, and the initial conditions were the starting setup. From there, everything else was just a matter of calculation. The universe was a solvable puzzle, and causality was the key that unlocked its secrets, revealing a future as fixed and certain as the past. This clockwork vision was both comforting and unsettling. It was comforting because it suggested that the universe was rational and orderly, not chaotic and meaningless. We could use the power of reason and mathematics to peel back its layers and understand its deepest workings. But it was also unsettling because it seemed to leave no room for free will. If every action was predetermined, were our choices just illusions? Were we simply cogs in a cosmic machine, playing out a part that was written for us billions of years ago? This vision of strict, unbending causality set the stage for one of the biggest revolutions in the history of science. Just as scientists felt they were on the verge of a complete theory of the universe, a strange new reality began to emerge. This new reality came from the world of the very small, the realm of atoms and the particles within them. This was the world of quantum mechanics, and it shattered the classical dream of a perfectly predictable clockwork universe. At this tiny scale, the old, comfortable rules of cause and effect seemed to break down completely. An electron, for instance, could suddenly appear on the other side of a barrier without ever passing through it. An atom could decay at a random moment with no specific trigger or immediate cause. This was a radical departure from everything that had come before. In the classical world, if you knew everything about a cause, you could predict the effect with 100% certainty. But in the quantum world, you could know everything there is to know about a particle, and you still couldn't predict its future behavior with certainty. You could only calculate probabilities. You could say there is a 50% chance an atom will decay in the next hour, but you could never say for sure when it would happen. It was as if nature had a built-in element of chance, a fundamental unpredictability that could not be erased, no matter how precisely we measured things. This quantum uncertainty wasn't due to our ignorance or clumsy instruments. The founders of quantum mechanics, like Werner Heisenberg and Niels Bohr, argued that this randomness was an inherent feature of reality itself. The universe, at its most fundamental level, was not deterministic. It was probabilistic. This idea was deeply troubling to many physicists, including Albert Einstein. He famously declared, God does not play dice with the universe. He couldn't accept that the universe was governed by chance. He believed there must be some deeper, hidden variables that we just hadn't discovered yet, which would restore the old reliable principle of causality. But over the decades, experiment after experiment has confirmed the strange predictions of quantum mechanics. The world of atoms and photons really does seem to operate on probabilities, not certainties. The neat chain of cause and effect that worked so well for planets and billiard balls simply dissolved at the quantum level. This forced a profound rethinking of what we mean by causality. If the fundamental building blocks of the universe behave unpredictably, then the perfect clockwork machine of classical physics was at best an approximation. The universe was not a predictable script. It was a story being written moment by moment, with an element of genuine surprise. We all live our lives assuming that causality is real. We flip a switch, and we expect the light to turn on. We put food in the oven, and we expect it to cook. This belief in cause and effect is one of the most basic assumptions we make about the world. It's the foundation upon which we build our understanding, our science, and our technology. Without it, the world would seem like a chaotic and magical place where anything could happen at any moment for no reason at all. Our minds are wired to see patterns, to connect events, and to look for the cause that explains the effect. But here is the surprising truth. Causality is not a proven fact of nature. It is an assumption. It is a starting point, a belief that we must accept before we can even begin to do science. The philosopher David Hume pointed this out centuries ago. He argued that we never actually observe causality directly. We only observe that one event consistently follows another. We see the lightning and then we hear the thunder. After seeing this happen many times, our minds create a connection and assume the lightning causes the thunder. But we never see the causeness itself, we just see a sequence of events. This makes our belief in causality something like an act of faith. It's a foundational belief that we cannot prove from first principles, but which we need in order to make sense of the world. In this way, it is similar to religious faith. A religious person might start with the belief that there is a God who created an orderly universe. A scientist starts with the belief that the universe is orderly and follows rational laws that can be discovered. Both begin with a fundamental, unprovable assumption about the nature of reality. Without this initial leap of faith, neither science nor religion could get off the ground. This doesn't mean that science and religion are the same thing. They use very different methods to explore their questions. But it does show that even the most rigorous science rests upon philosophical foundations that cannot be scientifically proven. The belief that the universe is comprehensible and that effects follow causes is the bedrock of the scientific enterprise. We assume it's true because it works. It allows us to build bridges, cure diseases, and send probes to other planets. But it remains an assumption, a powerful and useful one, but an assumption nonetheless. The universe hasn't signed a contract promising to always obey the law of causality. The principle of causality allows us to make powerful predictions about the world. We know that day follows night because we understand the cause, the Earth's rotation on its axis. This is a simple, reliable chain of cause and effect. We can predict the exact moment of sunrise and sunset years in advance with incredible accuracy. This is a triumph of the clockwork view of the universe. For large-scale events where the strange rules of quantum mechanics average out, the world does behave like a predictable machine. The orbits of the planets, the pull of gravity, the motion of a thrown ball, all of these can be described by deterministic laws. However, even in the classical world, our predictive power has its limits. Think about predicting the weather. We understand the physical laws that govern the atmosphere, the principles of fluid dynamics, heat transfer, and pressure. We have incredibly powerful supercomputers that can run complex simulations based on these laws, Yet we can still only predict the weather with reasonable accuracy a few days in advance. Why? Because the atmosphere is an incredibly complex system. A tiny change in initial conditions, a butterfly flapping its wings in Brazil, as the famous analogy goes, can lead to huge and unpredictable changes later on, like a tornado in Texas. This sensitivity to initial conditions is known as chaos theory. It doesn't violate the principle of causality. Every effect still has a cause. The problem is that the chain of causes and effects is so complex and tangled that it becomes practically impossible to predict the outcome. To perfectly predict the weather, you would need to know the exact position and velocity of every single molecule of air on the planet at one moment. This is an impossible task. So even within the classical deterministic framework, there are systems that are fundamentally unpredictable in practice, even if they are predictable in principle. This shows us that even without quantum mechanics, the dream of a completely predictable universe was always a bit of an illusion. The real world is messy and complex. Simple cause and effect relationships are often just useful approximations. While we can predict that night will follow day, predicting whether it will be a cloudy night or a clear one is a much harder problem. The cracks in the clockwork universe were there all along. Quantum mechanics just blew them wide open, revealing that the universe's unpredictability wasn't just a matter of practical limits, but a fundamental feature of reality itself. In order to make sense of a complex world, science often relies on building models. A scientific model is like a simplified map of reality. It's not the territory itself, but it's a useful guide that helps us navigate. When Newton developed his laws of motion, he imagined a world without friction or air resistance. He pictured perfect spheres moving through a perfect vacuum. In this idealized artificial world, his laws of causality worked perfectly. His equations could predict the motion of objects with absolute precision. This is a powerful technique that allows scientists to isolate a single principle and study it without the messy complications of the real world. These mathematical models are the backbone of physics. They create a kind of parallel universe, a world made of pure logic and equations where causality reigns supreme. In this world, everything is clean and predictable. We can describe the orbit of a planet as a perfect ellipse, even though in reality its path is slightly perturbed by the gravitational pull of other planets and moons. We can model a gas as a collection of tiny, perfectly elastic billiard balls, even though real gas molecules have complex shapes and interactions. These simplifications are what make the science possible. They allow us to see the underlying patterns. However, it's crucial to remember that these models are not the same as reality. They are artificial constructs, idealized versions of the world. When we apply these models back to the real world, we often have to add in correction factors to account for all the messy details we initially ignored, like friction, air resistance, and the unpredictable wobbles of quantum mechanics. The success of science lies in creating models that are simple enough to be understood, yet complex enough to make accurate predictions about the real world. It's a constant balancing act between simplicity and accuracy. So, when we say that science is built on causality, what we often mean is that our models of the world are built on causality. We create artificial systems where cause and effect are clear and unbreakable. These systems are incredibly useful and have led to all of our modern technology. But the question remains, does the universe itself really operate with the same clean, logical causality that we build into our mathematical worlds? Or is that just a feature of the maps we create, a reflection of the way our minds prefer to see the world, rather than the way the world truly is? Quantum mechanics forced scientists to build a new kind of model, one that looked very different from the clockwork machines of classical physics. In the quantum world, certainty is replaced by probability. The fundamental equation of quantum mechanics, the Schrödinger equation, does not tell you where a particle is. Instead, it describes something called a wave function. This wave function gives you the probability of finding the particle at any given location if you were to look for it. Before you look, the particle doesn't have a definite position. It exists in a haze of possibilities, a superposition of all potential locations at once. This is a profound shift in our understanding of nature. Imagine a weather forecast that, instead of telling you it will rain tomorrow, gives you a weather function that describes a 70% chance of rain, a 20% chance of sun, and a 10% chance of snow, all existing simultaneously. It's only when you open the curtains tomorrow morning, when you make a measurement, that one of these possibilities becomes real. This is how quantum mechanics describes the universe at its most basic level. Reality isn't a single, unfolding story. It's a branching tree of possibilities, and every measurement forces one branch to become the reality we experience. This probabilistic nature is not just a clever mathematical trick. It seems to be the way the world actually works. Experiments have repeatedly shown that particles like electrons can be in multiple places at once until they are measured. This means that the universe is not just unpredictable in practice like the weather. It is unpredictable in principle. There is no hidden information that would allow us to determine the outcome of a quantum event with certainty. The randomness is not a bug, it's a feature. The universe has an element of genuine, irreducible chance built into its very fabric. This has huge implications for the idea of causality. On the quantum level, we can't always say that A causes B. We can only say that A creates a certain probability of B happening. The old, deterministic chain of cause and effect is replaced by a web of probabilities. The universe is no longer a perfect clock ticking along a predetermined path. It's more like a cosmic game of chance where the rules are given by the laws of quantum mechanics, but the outcome of each roll of the dice is fundamentally random. This is the strange and wondrous universe that quantum physics has revealed to us. The limits revealed by quantum mechanics and the unprovable nature of causality point to a profound truth. Science cannot explain everything. There are fundamental aspects of reality that may lie beyond the reach of the scientific method. One of the most prominent examples is human free will. From a purely scientific perspective, your body and brain are physical systems made of atoms and molecules that obey the laws of physics. Every thought, every decision should ultimately be traceable to a complex chain of electrochemical reactions. In this view, your sense of freely choosing is an illusion. Yet, this scientific description fails to capture the most essential part of our experience, the feeling of being a person, a conscious self who makes choices and has intentions. We don't experience ourselves as biochemical puppets, we experience ourselves as agents. This is a deep paradox. Science, which is so powerful at explaining the objective world of objects, struggles to account for the subjective world of persons. The scientific method is designed to be third-person and objective. It cannot easily accommodate the first-person reality of consciousness and free will. Free will is not something that can be predicted or controlled by an external observer. This suggests that there might be more than one way of knowing the world. The scientific third-person perspective is one powerful way, but the first-person, subjective perspective of being a person is another. Perhaps causality, as science understands it, only applies to the world of objects, the world seen from the outside. Perhaps the world of persons, of subjects, operates according to a different principle. This is where the idea of an ideal intellect or an omniscient spirit becomes interesting. Such a mind could, in theory, know all things without the limitations of physical measurement. It could know the state of every particle without disturbing it, and perhaps even understand the mystery of free will from the inside. Ultimately, causality remains an indispensable guide for science, a tool that allows us to build an orderly picture of the physical world. But it is also an act of faith, a starting point that we cannot prove. Its limits, especially in the face of quantum uncertainty and the mystery of free will, suggest that our rational scientific models of the universe are not the whole story. They are maps of one part of reality, the enduring mystery of why there is an orderly universe at all, and our own experience as free, conscious beings within it points toward a deeper reality, one that may transcend the limits of human reason and the chains of cause and effect.